In this section, we're going to look at a conic section, specifically the ellipse.
Let's consider a cone. Now, mathematically, a cone is made up of two parts that look like kind of like an ice cream cone that you'd be familiar with since childhood. When you take two of these and stick them end to end, you form what we typically call a cone mathematically. Now, if you take a sharp knife and were to cut through this object, depending on which angle you cut through at, you would end up with a different result. If, for example, you cut simply straight across and you made a thin little slice right here, and you took that thin little slice, you cut once, and then just a millimeter below that you cut again, you'd end up with a circle. Circular cross section. This gives you a circle. Now, if instead of cutting directly across, let's say you cut at a very slight angle. So instead of having it be straight across, let's say it was something like this. Well, you would still have a similar object. You would still have something that's almost like a circle, except it would be slightly elongated in the direction in which you tilted your slice. You would end up with an elongated circle, more of an oval shape. Whenever you take a slightly angled cross-section of a cone, this is called an ellipse. Because both of these come from a cross-section of a cone, these are both referred to as conic sections. These are not the only conic sections, but for now we're going to talk specifically about the ellipse. Technically, a circle is a kind of ellipse where the amount of deformation is zero, where everything is exactly the same in all directions, whereas with what we would usually call an ellipse, it's longer in one direction than it is in another. So now, what is an ellipse? Well, it's a cross-section of a cone, the conic section that we get when we slice at a bit of an angle. Well, we can be a little more precise than that. We can define this without having to invoke the cone. Definition. An ellipse is the set of all points which we'll call P in the plane, meaning that even though the cone is a three-dimensional object, the conic section itself will not be in 3D. It'll be on the plane. It'll be on the XY plane. In the plane, the sum of whose distances from two fixed points, F1 and F2, these are called the foci of the ellipse. One of them is called a focus. If you take more than one, the plural of focus is foci, or depending on how some people pronounce it, foci. Either one would be acceptable. So the sum of whose distances from two fixed points, F1 and F2, is always some constant. The midpoint of the line segment that connects the two foci is called the midpoint of the ellipse. Oh, sorry, it's called the center of the ellipse. So, as I say, a picture is worth 1,000 words. Let's go ahead and take this description and look at it visually. So you begin with 2 points. Here's 1 point, and here's another one. Now, these don't have to be directly horizontal from each other. They don't have to be necessarily vertical from each other. In later sections, we'll talk about how they can be at a diagonal from each other. But for now, we're going to begin with one where they're directly across from each other, not at an angle. That takes a bit more effort. Huh? So here, we'll call this one F1, and we'll call the other one F2. It doesn't actually matter what you label them, just as long as they're both the two, each one's a focus, F1 or F2. Okay? Now, you're going to take a fixed distance. Say, for example, here on my ruler, let's say I want the distance to be 4. Okay, well, what I would want is the distance from here to here, that's 4 centimeters. Oh, but I don't want the distance from just one focus out. I want the sum of distances. So for example, this point right here, that would be 3 centimeters from this focus, and it would be 1 centimeter from this focus. And 3 plus that 1 would give me 4. So right here, I would say here's a point that if I take the distance from here to here, that's going to be some distance. I'll call it D2. Here for my example, I said, okay, that was 1 centimeter. And then here, this one, D1, that's 3 centimeters. So 3 plus 1 is 4. But now if I take another point out here somewhere, I could say that D1 and that D2 would add up to 4. And I could find other points. I could find lots of other points all the way around these two foci, such that if I take the distance from one focus to the point and from the other focus to the point, and if I add them together, always give me 4 centimeters or 10 centimeters or 6 centimeters or whatever distance I'm wanting to use. If I take all of those points, every single point that when I add together the distances gives me that common value, that forms an ellipse. Oops, I should include that point, shouldn't I? In history, some mathematicians have been known to be great artists. I am not one of them. Here, the center of the ellipse is, okay, now imagine you are connecting those two with a line segment from here to here. There is some point that's halfway in between those two. That is called the center of the ellipse. It's like saying the center of a circle, except the center of the circle, every point is equidistant from the center. Here, some points are closer to the center than others. So here, instead of relying on the points on the outside, we rely on these two focus, each of the individual focuses, foci. Like that. Whenever you have an ellipse, you will have your F1 and your F2. And again, they can be flipped around. You can have this one on this side, doesn't matter. And then in between those two, you'll have the center. You can make a line that goes through all of those points and comes out on either side of the ellipse. This is called the major axis. So here's a line that passes through the two foci and through the center. It comes out to touch the ellipse at 2 points. This is called a vertex. This is also called a vertex. You may remember the phrase vertex from when you study parabolas in college algebra. For a parabola, the vertex is the point where the parabola turns around. It's either the minimum if the parabola faces up, or it's the maximum if the parabola faces down. It's the same word, except parabolas have only one vertex, whereas these ellipses have a pair of vertices. One is called the vertex, plural, they're called vertices. This line that connects from this vertex to that vertex through the center, this is called the major axis. There is also a minor axis, which crosses also through the center, going perpendicular to the major axis. So the major axis connects the two vertices through the center. The minor axis is perpendicular to the major axis and also passes through the center. Now that we know how to define an ellipse, this definition can also show us what the equation to an ellipse is going to be. Note here that to define an ellipse, you have to start with 2 points and the distances from those 2 points to some other point out here. So for that, let's go ahead and recall from college algebra. Let's recall the distance formula. From some point x1, y1 to some point x2, y2. Then the distance is equal to the square root of the difference in the x values squared plus the difference in the y values squared. So recall the distance formula. And now let's see how we can use that distance formula to make this description into an equation. Let's begin by putting this on a coordinate axis. Coordinate axes are much simpler to use than to have to describe things as how far is it from here to here. Rather, you can simply give its coordinates. So let's begin with a coordinate axis. And let's have an ellipse on that coordinate axis. Here I've placed the center of the circle at the origin. And here I'm going to go ahead and place my 2 foci on either side of that center. Well, that makes things a little simpler because now the y-coordinate of the foci is going to be 0. It's going to be something comma 0. Here I'm going to call the distance from the center to the focus, I'm going to call it c. And that's a pretty common notation. Most books will call it c. Well, if that's positive c, well, now it's going to be negative c. So you've gone back a certain amount, okay, just like that. So now consider some point that is on your ellipse. It doesn't matter which point it is. So here, since I don't exactly know what it's going to be, I'm just going to call it xy. It's a generic point, somewhere on the outside. Now remember, you have to have a distance d1 and another one d2. Well, yeah, but we can find those because we can now use the distance formula to find the distance between xy and negative c comma 0, and also xy and c0. We can find those distances. Right? So I know that the distance d1 is going to be the square root of, well, that's the difference between those two. So that's going to be the difference between x and negative c. So x minus a minus c, I can show that as plus c squared, plus, and the difference in the y values, that's a y and that's a 0. Okay, so y minus 0, I can just write that as y squared, like that. Okay. d2, well, that's going to be the distance between this second focus and that point. So the difference between the x values, x and c, it'll give me x minus c squared. I'm subtracting them. Plus the difference in the y values, y minus 0, well, that's going to stay y. So those are the distances d1 and d2. Okay, now consider these points, the vertices. Here, I'll call this one a comma 0, and I'll call this one negative a comma 0. Right? After all, everything's symmetric, so if this one's to the right a units, this one's to the left a units. All right, now, whenever I add these two distances, they have to be a constant. So if I have the distance from here to here plus the distance from here to here, that's going to be the same as the distance from here to here and from here to here, or the distance from here to here and from here to here. Huh? Well, okay, that means that a0, since that's also on the ellipse, that has to be true for this point as well. Okay, so I want to find the distance from c0 to a0, and I want to add that to the distance from negative c0 up to a0. Well, notice this distance right here is the same as this distance back here. Okay, yeah, so, well, if this distance right here is the same as this distance over here, then the distance from negative C0 to A0, that's almost all the way across the ellipse. And then if I'm going to add this other little piece, that's the same as if I added this other little piece. So this gives me almost all the way across the circle, across the ellipse, plus this extra little bit. Well, that's all the way across the ellipse. So here, the distance from negative A0 to A0, that has to be the sum between D1 and D2. All right, well, from here to here, the distance from 0, 0 to A0 is A, so all the way across would just be double that. Okay, so D1 plus D2 must equal to double the value of A. All right? If I have this distance, I call it D1, plus this little distance D2, that little D2 is the same as this back here. So that's all of that plus that, that's just the distance all the way across. So the D1 plus the D2 is the distance all the way across. It's equal to 2A. So I can always take those and plug them in right here. I can find square root of x plus c squared plus y squared plus square root of x minus c squared plus y squared. That's equal to 2A. Now we can square both sides. Now here, if you're squaring this, remember if you have something like a plus b and you square it, that gives you a squared plus b squared plus 2ab. Okay, so if I square this first part, that just gets rid of the square root. Okay, so x plus c squared plus y squared. And then if I square b, if I square the second part, again, that's just going to get rid of the square root. That's going to be x minus c squared plus y squared is plus double the product of these two. So plus double the square root of this times this. So a plus b squared, that's your a squared, plus, there's your b squared, plus 2 times the a times the b. So I've gone ahead and squared this side, and that's going to be the same as squaring this other side. If I square 2a, that's going to give me 4a squared. So I've gone ahead and squared both sides. Okay, so now let's go ahead and isolate our radicals. Let's go ahead and subtract all that stuff over that way. So that's going to give us, I'm going to leave this stuff here right where it is, 2 square root of x plus c squared plus y squared times the square root of x plus, sorry, that should be a minus c. There you go. X minus c squared plus y squared is equal to, the 4a squared stayed right where it was, but now we're moving this stuff over this way. So we're going to subtract y squared and then another y squared. Okay, well that's minus 2y squared. And then we're subtracting both of these over this way. So that would be x plus c squared and then minus x minus c squared. Looks like that. We can always expand these and combine like terms. So that's equal to 4a squared minus 2y squared minus, if you square x plus c, that'll give you x squared plus c squared plus 2xc. And then if you square x minus c, that'll give you x squared plus c squared minus 2xc. Notice that some of these combined and some of them cancel out. So here you have negative 2xc, and then minus the minus makes that plus 2xc. So here these two simply subtract away, and all the rest of these double up. So this gives us 4a squared minus 2y squared. Those are gone. Minus x squared minus another x squared, that's minus 2x squared. And then minus c squared minus another c squared is minus 2c squared. Here I can divide both sides by 2. that gets rid of that 2. And since all those numbers are even, I get the division works out nicely. So if I divide both sides by 2, I get x plus c squared plus y squared, square root of x minus c squared plus y squared equals, and I'm cutting everything in half, so it'll give me 2a squared minus y squared minus x squared minus c squared, just like that. And now I can get rid of the square root by squaring both sides again. So let's go ahead and square both sides again. Like this. And that takes a bit of effort, so let's go ahead and take a look at how that works out. When we square on this side, that gets rid of the square roots. So that's going to give us x plus c squared plus y squared times, and again, that's going to get rid of that square root. So that'll give us x minus c squared plus y squared, like that, is equal to 2a squared minus y squared minus x squared minus c squared squared. And here's where it gets a little bit big. Here we can multiply this out. So this will give us x squared plus c squared plus 2xc plus y squared. We squared out that part, leave the y squared alone. And then over here we can square this out. That'll give us x squared plus c squared minus 2xc plus our y squared is equal to 2a squared minus y squared minus x squared minus c squared. Okay. So now here we distribute. And here is nothing more than distribution, right? You'd have this one times this one, this one times this one, this one times this one, and this one times that one, and so forth. Here, because of the limitation of my screen size, I think I'm going to share the results with you. I've gone ahead and just done this on a separate sheet of paper. And if we multiply that all out, we end up with c to the fourth minus 2c squared x squared plus 2c squared y squared plus x to the fourth plus 2x squared y squared plus y to the fourth. And that seems a little ominous. As I start writing this out and start getting into the more complicated stuff, we hear a large clap of thunder and a large bolt of lightning comes down. That seems a bit ominous. I think that means we're getting close to something important, yeah? Here, if we square this side, that equals 2. So here's the left side. And here it's going to be kind of big, so that's why I'm going to leave some extra space here. But this is the left side. And then the right side, once we square it, that's going to give us 4a squared. Oh, sorry, that should be 4a to the fourth. 4a to the fourth minus 4a squared c squared minus 4a squared x squared minus 4a squared y squared plus c to the fourth plus 2c squared x squared plus 2c squared y squared plus x to the fourth plus 2x squared y squared plus y to the fourth. Now, as big and cumbersome as that might look, you may notice we have a few terms that are like each other on either side of the equal sign, which means if I subtract c to the fourth here and c to the fourth here, that cancels out. And in fact, we see several of those throughout this expression, which means a lot of our terms are about to go away. So let's see what goes away. We have c to the fourth and c to the fourth. Now let's see here. We have 2x squared y squared and 2x squared y squared. We have y to the fourth and y to the fourth. We have x to the fourth and x to the fourth, like that. We have 2c squared y squared and 2c squared y squared. And oh, and here these don't quite cancel out. because they have opposite signs. Instead, they double up. So here I can add this over to this side. So I can say plus 2c squared x squared to one side of my equal sign, and plus 2c squared x squared to the other side of my equal sign. Here these cancel out, and now these come together. So all of this is gone, which means you're left with 0 equals. Now a lot of these are gone. You're left with 4a to the fourth minus 4a squared c squared minus 4a squared x squared minus 4a squared y squared plus 4c squared x squared, because here these two combine to give you this one. All the rest just stayed as they were. Notice that there's a bunch of 4's now, which means I can simply divide both sides by 4. Right? If I divide 0 by 4, it still stays 0. If I divide this side by 4, I just get a to the fourth minus a squared c squared minus a squared x squared minus a squared y squared plus c squared x squared. Notice that some of my terms have x's, some of them have y's, and some of them don't have x or y. So what we're about to do now is we're about to combine terms in such a way that the x terms go together, the y terms go together, and the constants go together. So here, let me go and take these two that have x's on them, and let's move them over this way. So let's add a squared x squared and subtract c squared x squared from both sides. Let's add a squared x squared and subtract c squared x squared from both sides. This gives me a squared x squared minus c squared x squared is equal to, you know what, let me do the same thing for my y value. Let me go ahead and add a squared y squared to both sides. So plus a squared y squared. And so now this one's gone, and this one's gone, and this one's gone, leaving me only this one. That leaves me a to the fourth minus a squared c squared. Okay. Notice these have a common factor of x squared, which means I can write this as a squared minus c squared times x squared. All right, I factor out my x squared plus a squared y squared. And here I have a common factor of a squared, which I can factor out as a squared times a squared minus c squared. From a very complicated looking equation before, you realize that almost everything cancels out and you're left with something fairly simple looking, at least compared to what we had before. Now, one thing to notice is that a squared minus c squared appears more than once within this equation. Okay, well, a squared minus c squared. Is there anything we can say about that? Well, going back to our picture, notice that a is bigger than c. All right, a is further to the right over here, or here it's further to the left. A positive a is bigger than a positive c. Okay, well then that means a squared is bigger than c squared. Okay, so, well that means a squared minus c squared has to be positive. If a squared is bigger than a bigger number minus a smaller number, it has to give you a positive. So here, note, a squared minus c squared we know will be positive. And since it's a positive number, it's the square of something else. Now, it doesn't have to be a perfect square, you know. A squared minus c squared might be 25, in which case it's the square of 5. Or it might be 7. But you know what? 7 is also the square of something. It's the square of the square root of 7. So even though it's not a nice square root, it's still a square root. So here, because this is positive, we can take a squared minus c squared and call it the square of something else. And here, let's remember that one, because that will come in handy in a moment when we start looking at examples of this result. So here, we can replace that a squared minus c squared, and that a squared minus c squared with something else which we're calling b squared. Now, you could leave it as a squared minus c squared, but it'll look a little nicer and be a little simpler to work with here in a moment if we replace it with b squared. And we'll see how it's easier to work with here in a moment. And although this is a nice result, we typically write it in a slightly different way. We know a squared and b squared are just constant numbers, which means a squared times b squared are also just constant numbers, which means we can divide on both sides by a squared and b squared. Here, the a squared cancels with the a squared. Here, the b squared cancels with the b squared. And here, a squared b squared over itself is equal to 1. So this leads us to the final result, x squared over a squared plus y squared over b squared is equal to 1. This is the form of the equation of an ellipse. Equation of an ellipse, where a is the distance from the center to the vertex, and it doesn't matter which vertex, since it's symmetric, it goes on either direction. From the center to that vertex to that vertex, it's all the same. That is the distance from the center to the vertex, either one. And b, well, that's equal to, I guess I should say b squared, because that's what we have down here. Here, let me just write that as b squared is equal to a squared minus c squared. And c is the distance from the center to a focus. Which means that if you can uniquely determine, if you can determine what the distance is from the center to the vertex and from the center to the focus, well, putting those together will give you what b is, and that will uniquely determine the equation of your ellipse. You may recall from college algebra that when you have the equation of a circle, it looks something like this: x squared plus y squared equals r squared. Right? Here, if both of these numbers were the same, then you would have, you could multiply, say, instead of calling it a squared and b squared, since they'd both be the same, you could call that a common thing. For example, r squared. And if you multiply the r squared over, you would have the equation of a circle. What that means is that this being different from this one, these a and these b being different, are what tell you that you have not just a circle, but an ellipse. It's been deformed in one direction or another. One other thing to note is that if you examine a simple sketch of an ellipse, let's say, for example, we set x equal to 0. After all, they're both variables. I can set one to a number and solve for the other. So if I set y equal to 0, well then, in order for this to equal to 1, a and x have to equal to each other or be opposites of each other. Here, either x has to equal to a or negative a. Okay, well then that means that over here I must have either positive a or I have negative a. Okay, well I knew that. That's what we labeled the vertices of an ellipse, positive a and negative a. Okay, and again, we get that when y is equal to 0. If y is equal to 0, then for this to be true, x is either equal to a, because a squared over a squared is 1, or negative a, because negative a squared, the negative goes away from the square, over a squared is equal to 1. But notice what happens when I set x equal to 0. Well, then that means I'm on the y-axis. And in order for this to be true, in order for this to equal to 1, my y has to equal to b, because b squared over b squared is 1, or it has to equal to negative b. Oh, but we had a name for the line that goes from the that goes through the center of your ellipse, and that is perpendicular to this line between your vertices. The line between your vertices we call the major axis, and this line that's perpendicular to it through the center is called the minor axis. So not only is b an artifact of the values for the distance from the center to the vertex and the center to the focus, but also in its own right, it is a distinguishing feature of the ellipse. Because after all, b squared is found by taking a squared minus c squared, but also B is the distance from the center, either up or down. Now, keep in mind later on we'll have these rotated, we'll have these not necessarily being lined up perfectly to the axis. So distance from the center in either direction along the minor axis. Oh, I won't be able to fit that in here. In either direction along the minor axis. My apologies, I planned that poorly. B is the distance from the center in either direction along the minor axis. So here's my center, up or down by B units. One other thing you may remember from college algebra is that when you have the equation of a circle, you can offset the equation of the circle to have a different center by adding or subtracting to the value of x and y. Recall, if you have x squared plus y squared equals to r squared, that's a circle of radius r and center 0, 0. However, if you had something like x minus h squared plus y minus k squared is equal to r squared, that was a circle, still of radius r, but this time the center is not at the origin, it's at h and k. The same thing happens here. If we modify these values of h and x and y with some values, which we're still going to use h and k because that's the familiar value that we use for a circle, then that will give us not only an ellipse, but an ellipse centered somewhere else besides the origin. So with all of this, we now have developed the equation for an ellipse. Let's go ahead and summarize that. If you have x minus h squared over a squared plus y minus k squared over b squared is equal to 1. This is an ellipse. Okay. It's going to be centered at h comma k, h and k. The distance, the value a is the distance from the center to either axis, not either axis, either vertex. B is the distance from the center to either, let me say in either direction, in either direction along the minor axis, where C is the distance from the center to either focus, and there is a relationship between these values, namely that a squared, I'll write it this way, b squared equals to a squared minus c squared. And visually the way that looks is again, your ellipse may not be at the origin, it may not be centered at the origin, it's going to be somewhere, centered somewhere, where here your center is HK. You're going to have a focus on either side of that center HK. The distance from here to here or here to here will be C. The distance from the center out to the vertex, that will be A, and the distance from the center up along the minor axis, that'll be B. So that's your A all the way across, that's your B all the way up, and that's your C. And of course your B is also down, your A is also to the left, and your C is also to the left. So everything's symmetric. Here I've only drawn these parts. Note that sometimes your A and your B will have a different size. The sizes will be flipped. Normally your A is bigger than your B, right? Because you're, A squared minus C squared. Okay, well then A squared is bigger, and if you subtract it, B squared must be smaller. However, sometimes you'll have this number be bigger than this one. That doesn't mean it's not an ellipse. It doesn't really change much of anything. It just means that now your major axis is going up this way. In other words, you've gone up further than you've gone left or right. Oh, then that means that this one should be the major axis. The major axis is whichever one's the longest. Okay? So let's take a look at some examples of this. The first one is, let's go ahead and graph. The question is to graph the following equation. Let's go with 9x squared plus 4y squared is equal to 36. Okay? Now, notice this almost looks like the equation of a circle. Right? X squared plus y squared equals 36. The fact that these numbers are different is what tips you off to this being an ellipse. The ellipse and the circle will both have something squared plus something squared. The difference is with the circle, these numbers are either not going to be there, or if they are there, they're both the same, 4 and 4 or 9 and 9. But if these numbers there are different from each other when you're adding, that's what tells you it's an ellipse. Note that an ellipse always has this equation equal to 1, so let's begin by dividing both sides by 36. Here this gives us 9 divided by 36, that's 1/4. So that'll give us x squared over 4 plus 4 over 36, that's 1/9. So y squared over 9 equals to 1. And there we go, that's all we need. We now know that since nothing's being subtracted from h or from x or y, there is no h or k, so we know our center is at the origin. We have our, notice that y squared is over a bigger number than the x squared. Okay, well then that means that our major axis will go along the direction of the y-axis instead of the direction along the x-axis. So let's see here. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and 6. Okay, so we know our center is at the origin. The distance from the center to either side of the vertex, that's given by your a squared. Notice here a squared, which is underneath your x squared, that's actually smaller than this one. So in this case, this won't be the major axis, it'll be the minor axis. Still, 4 is your a squared. Okay, well then a must be the number 2. It's the square root of that. So from your center, you're going to go 2 steps in either direction, and those will be on your ellipse. 2 steps in either direction. Now if you go 3 steps in either direction along the y-axis, 1, 2, 3, and 1, 2, 3, there's your major axis. If that's a little confusing, if that's going to be a problem where, I have a hard time keeping track of which one is A and which one's B, you can also do this. Okay, if y is equal to 0, that means I'm on my x-axis, then what are my solutions? Oh, well, for that to equal to 1, x is either positive 2 or negative 2. Yeah, there you go, positive 2 or negative 2. If x is equal to 0, meaning I'm on the y-axis, what do my solutions have to be? Oh, well, for this to equal to 1, y is either equal to 3 or negative 3. Oh, positive 3 or negative 3 along the y-axis. Either way, here's your major axis, that's the longer one. Here's the minor axis, here's the shorter one. Here's our ellipse. Finally, every ellipse is determined by its center and by the points on the outside, but also a important part of every ellipse, in fact every conic section, we'll see some in later sections, is where the focus is. So here let's also talk about where the focus is. Remember, the focus is in line with the major axis, which is the longer of the two axes. Okay, so I know each of my foci will be somewhere along here, since that's my major axis, the larger one. Okay, so now I just need to know how far along. Okay, well, that's what this equation's for. I know that b squared is equal to a squared minus c squared. Okay, well, I already know my a and b. I need to find my c. I need to find the distance from the center to the focus on either side. Okay, well then solve for c. If I have b squared is equal to a squared minus c squared, that's the same as saying I can go ahead and add my c squared over this way and subtract my b squared over this way. So c squared, now on this side, is equal to a squared, and I'll subtract the b squared over this way. C squared is equal to a squared minus b squared. But I know that my a squared and my b squared are going to be 9 and 4. Remember, this has to be a positive since it's the square of something, so make sure you don't end up with a negative. Here that means c squared is equal to, a squared must be the bigger one, so that's your 9. And c squared must be the smaller one, that's your 4. And this gives you 5, which means that c must equal to the square root of 5. The square root of 5 is 2 point something. Right? It's a little bit more than the square root of 4. Oop, my calculator seems to have died. There we go. So if I wanted to have a decimal approximation, it's about 2.2. So right here, I could say, okay, that's going to be up 1.2. 1.2. But I wouldn't label it as 2.2. I would label it as the square root of 5. So 0 root 5 and 0 comma negative root 5 in either direction. And there we go. That's a complete graph. We have our ellipse along with its center and its foci. All right. I think you might give this a try then. For the next one, go ahead and give this a try. You're going to graph. All right, let's try x plus 3 squared. Now notice now it's not just x squared, it's x plus 3. That means your center will move to somewhere else. Okay, so x plus 3 quantity squared plus 4 times y minus 2 quantity squared. And that's equal to 16. All right, so go ahead and pause the video and give that a try. Just give yourself the time that you need, and once you have a graph along with the labeled foci, go ahead and unpause the video and we can go through it together. All right, so let's take a look now. We begin with our center. Notice that that's x minus a minus 3. Okay, so that means our center will have negative 3 as its x coordinate. And here that's y minus 2, so that'll have 2 as the y coordinate. If that's a little confusing, you might also remember that by saying, what values do I plug in to make these 0? Well, I would plug in negative 3 to make this 0, and I'd plug in a positive 2. So here my center is at negative 3, positive 2. So let's begin with that. So our center, negative 3, positive 2, will be right there. Note that we do have to now divide everything by 16. We could have done that before or now. It doesn't affect the center at all. And by dividing everything by 16, we now put this in the standard form for a ellipse, or for an ellipse. So this would be x plus 3 squared over 16. Note 16 can also be written as 4 squared if you want to make it look even more like this, something squared. If you write it as 16, that is fine. Just like I wrote these as 4 and 9 instead of 2 squared and 3 squared. However, you can also write it as 4 squared and, in this case, 2 squared if you want to make it look even more like this form here. In any event, you'll still get the same result. Here, if we divide this by 16, 4 over 16 is the same as 1 over 4. So that'll be y minus 2 squared over 4, which is the same as 2 squared. So if you write 16 and 4, that's fine. 4 squared and 2 squared will mean the same thing. Okay? So now, here, that's our bigger number, which means that our major axis will be along parallel to the x-axis. If that's your center, well, then that's telling you that your major axis is 4 units along the x-axis from your center. So from here, I'm going to go left, 1, 2, 3, 4. And I'm going to go right, 1, 2, 3, 4. Now my minor axis, I'm going to go 2 steps in either direction from my center. 2 squared, that was our 4 right from before. So it's going to be 2 steps up, 1, 2, and 2 steps down, 1, 2, right here on the y-axis. So now that we have our major axis and we have our minor axis, we have what we need to graph our ellipse. Now, the last thing we need to find out where our foci are. And we can do that by noting that b squared is equal to a squared minus c squared, which we can rearrange however we like. And of course, what we need is, since we already know our a and our b, we need to find what our c is. Here we can take b squared equals a squared minus c squared. And as we saw earlier, that's the same as saying c squared is equal to a squared minus b squared. All right, so here we go. Here's our a squared. It's always the larger of the two. This has to be a positive. Otherwise, you couldn't square something to give that. You couldn't square a real number to get that. So here, our a squared, that's our 4 squared, in other words, 16, minus our b squared, that's our 2 squared, in other words, 4, and this gives us 12. So if c squared is equal to 12, that means c is equal to either plus or minus the root of 12. I guess up here I should have said plus or minus, right? Either way, you know it's going to be on both sides. So we know that our focus must be on the major axis. In this case, the major axis goes left and right because that's the longer one. And so we're going to take square root of 2 steps in either direction from that point. All right, the square root of 2, that's, the square root of 12, that's about 3.5, give or take. So we're going to go in either direction about 3.5. 1, 2, 3.5. And over here, 1, 2, 3.5, give or take. Now, we don't actually label those as 3.5 or whatever. Rather, we label them as using the exact value. So here, this starts off as what? Negative 3, 2. It still has the same y value because you haven't gone up or down to get to these points. But you've either gone to the right or to the left the square root of 12 units. So here, this focus would be at negative 3 plus root 12, comma 2. From negative 3, you went to the right 12 steps, or root 12 steps, rather. And then from here to this other focus, you took negative root 2. You went to the left. So that's going to be minus 3 minus root 12, comma 2. Right? And there is our ellipse. We have our 2 vertices. We have the points on either side of our minor axis, and we have our 2 foci on either side of our center. And that's our result. Okay. Another kind of example we can look at is we may have an ellipse where the equation is not in such a nice form where you can simply either say, okay, it's x squared over a squared plus y squared over b squared equals 1, or something where you can just divide and get to that point. You may have an equation that's in the general form of a conic. We'll talk about what we mean by a general form of a conic in later sections when we actually introduce more conics. For now, we're simply going to start off with an equation that doesn't quite look like what we want it to. So let's consider the question. Let's go ahead and graph 4x squared plus 9y squared minus 32x plus 36y plus 64 equals to 0. What we would like is we would like to have our ellipses always look like this. X minus h squared over a squared plus y minus k squared over b squared equals to 1. This is called the standard form. This doesn't look like that. Right? Even if we take the constant and move it over, it's these terms that cause the problem. We're not supposed to have any linear terms. Everything's supposed to be quadratic. This is called the general form of a conic. We're going to worry about this more in later sections when we actually start talking about other conics. But for now, the thing to point out is that even in this form, where we have these extra linear terms, you still have x squared plus y squared. And yeah, you have some numbers here. Still, x squared plus y squared. That's what tells you that you're beginning with a ellipse. And you say, well, what are the other options? Well, again, we'll see those when we look at other conics in later sections. For now, let's consider what we would do to make this look like that. Okay, well, you may remember from college algebra the concept of completing the square. That's how we found the center of a circle. That's how we found the vertex of a parabola. And that's how we're going to find our standard form of our ellipse. All right, so let's go and do this. To complete the square, we're going to begin by rewriting things so that we can bunch our x terms and our y terms together. Take your constant and move it over to the other side. So here, we're not really changing anything yet. We're just regrouping some stuff. So we're going to take 4x squared minus 32x. Leave a little space here because we're going to fill it in here in a moment. Plus 9y squared plus 36y. Again, we're just grouping our y terms together. And then let's take our 64 and move it over to the other side. Move whatever constant you have over to the other side, because eventually you're going to want that to be a 1. So that's going to go away, and you're left with negative 36. All right, so now we're going to complete the square. You're going to take the two terms that have a common variable, and you're going to factor out the lead coefficient. Now, notice you can also factor out an x, but you're not going to. You're just worried about the number here. So what you're going to do is you're going to take 4 and factor that out. If you factor 4 out of these two terms, you're going to get x squared minus 8x. You're going to do the same thing for these two. You're going to take those two and factor out the lead coefficient. Again, I know I can factor out a y, but I'm not going to. Just the number. So that's going to give me plus 9 times y squared plus 4y. And then over here, we haven't done anything yet. The next thing you want to do is you want to complete the square. The way you do that is you take whatever number is in front of your x. You're going to take the linear coefficient. You're going to cut it in half and then square it. And that's going to go right here. Half, then square. And same thing for this one. You're going to take half, then square. All right, well, half of negative 8 is negative 4. And when you square negative 4 times negative 4 is positive 16. In fact, let me go ahead and write that in red here. Same thing with this one. Half of 4 is 2, and square 2 gives you 4. So plus 4. But notice it changes the nature of your equation. If you compare this to the original equation, it's different. 4x squared, okay, that's fine, 4x squared. 4 times negative 8x, that's negative 32x. Yeah, that's fine, I had one of those before. But then when I multiply 4 times 16, that's 64. Oh, what did I do here? Why did I subtracted 64 from both sides, and for some reason I wrote negative 36. I have no idea why I just did that. I'm just noticing that right now. That was not to prove a point. That was not to do anything. That was legitimately an oversight. My apologies. 0 minus 64 is negative 64. All right. Let's go back to this part over here. So here we say, okay, 4x squared. Okay, that's fine. we've got negative 32x. Okay, great. But then 4 times 16 is 64. But we don't have a 64 anymore. No, on this side, right, we moved it. We moved it over there. So here we have an extra 64. We added 64 to this side, which we never did to the other side. Oh, well, then we do it to the other side. With an equation, whatever you do to one side, you do to the other. 4x squared, that was already there. Minus 8x times 4, that's negative 32x. That was already there. But 4 times 16 is 64, which we didn't have before. So if I'm adding something to this side, I need to add the same thing to the other side. Same thing over here. 9 times y squared. Well, I already had 9y squared. That was already there. 9 times 4y is 36y. I already had that. Okay, cool. 9 times 4 is 36. I didn't have a 36 here. Okay, so that's new. I've added 36 to this side of my equation. So whatever I do to one side, I got to do to the other side. Plus 36. Notice it now. This is a perfect square. You can factor it. This factors down as x minus 4 times x minus 4, or more simply, x minus 4 squared. This factors as y plus 2 times y plus 2, or more simply, y plus 2 squared. And over here, these are all constants. You can just combine them. Negative 64 plus 64, that's 0. 0 plus 36, well, then that's 36. Oh, but now that looks almost just like that, except that shouldn't be a 36. That should be a 1. Okay, well, we know how to do that. We divide both sides by 36 all the way across, and that gives us our result. So now we have x minus 4 squared over 4 over 36. That's the same as 1 over 9. And 9, I can just write that as 3 squared if I like. Plus plus y plus 2 squared. 9 over 36, that's the same as a quarter. So that's going to be over 4. And 4 is the same as 2 squared. And then here, 36 divided by 36, that's the number 1. So now that looks exactly like what we wanted. That's a standard form. So now we can go ahead and graph this. We have that our center is going to be at 4, negative 2. Just like that. We have that our value of a, that's going to be 3, which means we're going to travel 3 units from the center along the major axis. The 2 tells us we're going to travel 2 units from the center in either direction along the minor axis. So we can now graph enough points to create our graph. So our center is at 4, negative 2, 4 to the right and down by 2. We're going to travel 3 units parallel to the x-axis, and that'll be our major axis since that's the larger number, 1, 2, 3, and backwards, 1, 2, 3. We're going to travel 2 units perpendicular to that axis along our minor axis. We're going to travel up 2 steps, so that'll put us right on the x-axis, and then down 2 steps. That'll be down here, and then that forms your ellipse. Finally, you can find your foci. We know that c squared is equal to a squared minus b squared, which in our case will be a squared, that's 3 squared, which is 9, minus b squared, that's 2 squared, which is 4, and that'll give us 5. So since c squared is equal to 5, that means c is equal to plus or minus the root of 5. So from here, we're going to travel along the major axis. Foci are always along the major axis, whichever of the 2 is the longest. And now we can travel in that direction the square root of 5 units, which is about 2.2. So 1, 2, and a bit, and back 1, 2, and a bit. We can label those points. We know this was the point 4, negative 2. These will have the same y value, but the x value will either add or subtract root 5. So the one on the right will be 4 plus root 5, comma, negative 2. And the one on the left will be 4 minus root 5, comma, negative 2. Just like that. And this is our graph. Notice that finding this graph depends on not just what we saw in the last few problems, but also on writing our result in this form by completing the square. Okay, so let's go and give that a try. Let's have you graph 9x squared plus 25y squared minus 36x plus 50y minus 164 is equal to 0. Obviously, this cannot be graphed as it currently rests. However, if you can write that in the standard form by completing the square, then you can graph this one the same as we've graphed the last three. So go ahead and give that a try. Pause the video, give yourself whatever time you need, and once you're done, go ahead and unpause the video, and we can go through this one together. All right, so let's take a look. We're going to begin by rearranging these so that our x terms are together and our y terms are together. So 9x squared minus 36x plus 25y squared plus 50y. And then we're going to take our negative 164 and add it to the other side to give us positive 164. Okay, so now what we want to do is we want to complete the square on each of these pairs, here and here. Completing the square here, we're going to begin by factoring out the 9. That'll give us 9 times x squared minus 4x. And then once we factor out the 9, we can complete the square in here. We complete the square, we take that number, cut it in half. Half of 4 is 2, and then square 2 gives us 4. But by adding 4 in there, what have I really done? Well, 9 times x squared, that was already there. And 9 times negative 4x, that's negative 36x, that was already there. But 9 plus 4 is 36. I don't have a 36 here. So that's new. I've added 36 to this side of the equation, which means I have to add 36 on this other side. I can do the same thing for these two. I can factor out, notice both of those, I can factor out 25, factoring out the lead coefficient. If I factor out my 25, I get y squared plus 2y. Again, note, I know I have a common y, but I don't factor that out, just the number. And now I complete the square by taking half of that, half of 2 is 1, and square 1, well, that's still 1. But again, that's new. 25 times y squared, I already had that. 25 times 2y, that's 50y. I already had that. But 25 times 1 is 25. I didn't have a 25. That's new. Okay, so since I just added 25 to this side of the equation, I have to add 25 to the other side of the equation. But now, this can be factored down. Let me leave my 9 as it was. Here, this factors as x minus 2 times x minus 2, or more simply, x minus 2 squared, plus 25 times. This factors as y plus 1 times y plus 1, or more simply, y plus 1 squared. And these are just regular numbers. 164 plus 36 is 200, plus another 25 is 225. And now that almost looks like what we want, except that in the standard form, the ellipse should have this constant be 1. So over here, I need to divide everything out by 225. And so now we can reduce these down. 9 over 225, that's the same as 1 over 25. So that's, instead of 9 over 25, I'll just write this thing over just 25. That reduces to 1 over 25. And 25 really is just 5 squared. So I'll write it that way so that I know what my a is. Plus y plus 1 squared. 25 over 225 is 9. All right, it's 1 over 9. So here I can write that over 9. And 9 is the same as 3 squared. And here, dividing a number into itself, that's the number 1. So this gives us everything we need to now graph our equation. We have our center, which is 2, negative 1. Now you can plug in a 2 to make that 0. You can plug in a negative 1 to make that 0. We know it's an ellipse, and now since we know our a and b, we know how far we're traveling along parallel to the x-axis. Since that's the bigger number, that's our major axis. And parallel to the y-axis, that's a smaller number, so this will give us our minor axis. Our center is 2, negative 1. So 2 to the right down by 1. That's the bigger number out of our, so that's going to be our a out of our denominators. So that means that our major axis will travel parallel to the x-axis 5 steps. 1, 2, 3, 4, 5. And left 1, 2, 3, 4, 5. So there's our center, 2, negative 1. Traveling 5 steps in either direction gives you your vertices. If you now then travel 3 steps from your center perpendicular to that major axis, you'll find the points on the either side of your minor axis. 3 steps up, 2, 3, and 3 steps down, 2, 3. This now gives us our ellipse. And finally, we can find where our foci are going to be. We know that c squared is equal to a squared minus b squared. Or in other words, c squared is equal to, there's your a squared, the bigger of those two denominators, 25, minus the smaller of those two denominators, that's 9. 25 minus 9, that's 16. And if c squared is equal to 16, that means c is either equal to plus or minus root 16, which that's just plus or minus 4. So from your center, you're going to travel along your major axis. Again, your foci are always laying on your major axis. And from that center, you're going to travel along the major axis 4 units in either direction. So that'll put you 1, 2, 3, 4. That'll put you 1, 2, 3, 4. So here, these are nice whole number coordinates. That is what? 2, negative 1. These are still going to have that same negative 1 as your y-coordinate, but now if you're starting at x equals 2 and you go 4 to the right, that's 3, 4, 5, 6, comma, negative 1 as one focus, and 1, 0, negative 1, negative 2, comma, negative 1 as your other focus. And there we go. Okay, finally, for this section, we can go backwards. So far, we've started with equations and found a graph. But you can also start with a graph, or at least a description of a graph, and create an equation. For example, let's go ahead and find the equation of an ellipse. And of course, this could be given as a drawing, or it can be given just as a description. Here, I'll give it as a description, where the major axis has endpoints 2, 2, and 8, 2. And the minor axis has endpoints at 5, 3 and 5, 1. Okay. If this is given as a drawing, oftentimes that drawing is useful. If it's given as a description, you may wish to create a drawing anyway. Here I'm going to draw it because it's easier to explain how all these things fit together through a graph. However, you'll see as we go through it that even without the graph, you can still do the same thing. Okay, so we're going to have a few points of interest. 2, 2, that's one point of interest. 8, 2. 5, 3. 1, 2, 3, 4, 5, 3. And 5, 1. And we're going to have an ellipse where those points give us our major and our minor axis. Well, note that our major and our minor axis intersect at the center. Well, that's one of the things that we need. We're going to need to fill in x minus h squared plus y minus k squared. This one over a squared, and this one over b squared equals to 1. So we need to find our h, our k, our a, and our b. Okay, well, one thing we need is our center, h and k. Well, notice that's where these cross. Okay, well, here, this entire line is made up of points that have the same y value. In this case, 2. That's 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2. Okay, so I know that my y coordinate must be 2. Well, all of these points are made up of, this line is made up of points where 5 is the first coordinate. All right, 5, 1, 5, 2, 5, 3, 5, 4, and so forth. So the point where they intersect must be where the x values are always 5 and the y values are always 2. Oh, 5, 2. Notice I don't really need the picture for that. Here, look, my x values are always 5. My y values are always 2. The only place where those intersect are 5, 2. Now, if you do have your illustration, of course, you can always just count off, right? 1, 2, 3, 4, 5, up, 1, 2. Oh, either way, my center is at 5, 2. Once I have that, finding a and b are simple. The major axis, well, that's the longer one. And to go from 5, 2, let's see, we need to go in either direction. We'd go 1, 2, 3 steps to the right, or 1, 2, 3 steps to the left. Either way, our value of a must equal to 3. Remember, a is always the larger of the two. Here, b must be the smaller axis. And from here, I would travel up 1 step or down 1 step. Either way, b is equal to 1. So now taking all that information, we have our result. We have x minus 5 squared over 3 squared plus y minus 2 squared over 1 squared is equal to 1. Or you can also write that as, of course, 9 and 1. So you can write this as x minus 5 squared over 9 plus y minus 2 squared. Dividing by 1 doesn't change anything, so oftentimes you would just leave it the way it is. However, some people prefer to write the 1. Either one's fine. And anyway, that's equal to 1. So this is our equation of the ellipse described here. Notice the picture does come in handy to explain where everything fits together. However, you note that you could have done it even without the illustration. All right, so go ahead and give this a try. As our last problem for the section, go ahead and find the equation of the ellipse, which has foci at -5, 0, and 5, 0. And which has vertices at -8, 0, and 8, 0. For this one, whenever you have a focus, notice that your A and your B are giving distances along your major and your minor axis. Your focus is not actually given as part of your equation, but it's not unrelated. Recall that the relationship between C, A, and B is such that C squared is equal to A squared minus B squared, or any rearrangement thereof. So this will come in handy when we try that one. So go ahead and give this a try. Of course, you are going to have an equation that looks like x minus h squared over a squared plus y minus k squared over b squared equals 1. And what you need to do is find your h, your k, your a, and your b. You may find that an illustration is useful here, although at the end you'll find it's not strictly necessary. It may be a good idea to use one anyway. So go ahead and pause the video now. Give yourself whatever time you need. And once you're done, you can unpause the video and we'll go through those together. So, as mentioned, we may wish to start with an illustration. Again, it's useful in helping us organize our thoughts. However, it's not strictly necessary. All right, so let's go ahead and take a look here. -5, 0. And 5, 0. Those are the location of two of our two foci. -8, 0, and 8, 0. Those are the location of our vertices. Okay, well, that means that our major axis must be along the x-axis. So here, that means that underneath the x minus h squared, that's going to be where the bigger number goes, because the bigger number tells you which direction your major axis falls on. If the bigger number is under the x squared, well, then your major axis is parallel to the x-axis. If it's under the y squared, well, then it's parallel to the y-axis. Okay, first of all, our center. Notice that these 2 points are equally distant from the origin. Halfway between these two vertices, halfway between these two foci is the origin. 5 in either direction, 8 in either direction. So here our center is at the origin. Of course, you could see that without the illustration. Hey, look, 5 units in either direction. Oh, well then, 5 units in either direction of what? Oh, of the origin, of 0. Or if you prefer, you can say, what's the average of these two? The halfway mark between two numbers is their average, right? Here. Halfway between 2 and 8. Well, that's the average of 2 and 8, which is 5. Hey, that's that 5 right there. Halfway between 3 and 1, that's the average of 3 and 1, which is that 2 right there. Halfway between two numbers is the average. So if you average -5 and 5, you get 0. If you average -8 and 8, you get 0. So either way, your center is at 0. Okay? So here, our h and our k, those are going to equal to 0, 0. Okay. What about our value of a? Well, again, a is simply the distance from the center to either of your vertices. So here, that's 8 units. Or if you prefer, you can go this way. Either way, that's 8 units. So a has to equal to 8. Okay? But now b is the distance from the center along your minor axis in either direction. We don't have that. We're never told that. But right here, that c is the distance from your center to one of your foci. And again, it doesn't matter which one. And we know that one. So since we have c squared is equal to a squared minus b squared, we have our a and our c. We're just trying to find b. Okay, so we can solve for b. We add b squared over this way and subtract c squared over this way. That means that b squared is equal to a squared minus c squared. but I can fill those in. I know that A is going to equal to 8. So that'll be B squared is equal to 8 squared minus, here's C, the distance from the center to a focus. That's going to be 5 steps in either direction. So here we know that our C is equal to 5. So that means that B squared is equal to 64 minus 25. And so that gives us what, 39? 39. And so here B squared must equal to the square root of 39. B squared is equal to 39, which means B is equal to either plus or minus the root of 39. Root of 39 is 6 point something, right? I know the root of 36 is 6, so the root of 39 must be slightly bigger than that. If I take 39 and take its square root, yeah, it's just a little bit bigger than 6. So 6.2-ish. 1, 2, 3, 4, 5, 6, and a bit. And then down 1, 2, 3, 4, 5, 6, and a bit. Right about there. We're not being asked to draw this, but just to give a little closure to our result here. So we know that B is equal to plus or minus the root of root 39 here. So our B squared is just that 39, and so now we have everything we need. We have that our equation is x minus h. Well, since h is 0, we can just leave that as 0. I'm going to write that as 0 for now, and then I'll simplify in a moment. So that's x minus h squared over a squared plus y minus k squared, our k is also 0, over, we're not using this 5, we're using this root 39, because that's your b. All right, 5 is your c, and that's being squared, and that equals to 1. But then that simplifies. X minus 0, that's just x, that's being squared, over 64, equals y minus 0, that's just y. Oh, sorry, that should be a plus, not an equals. Plus y squared over. The square and the square root cancel out, giving you just 39 is equal to 1. And that is our result. So this is the equation of this ellipse, which has negative 8, 0, and 8, 0 as its vertices, and negative 5, 0, and positive 5, 0 as its foci. And just to give us a little bit of closure here, let's go ahead and actually see our ellipse. Just like that. And that makes us happy. So that brings us to the end of our section and our topic. If anybody has any questions, comments, or problems, please reach out. Let me know, and I'll get back to you as quickly as I can. And I hope everyone has a nice day.